Our first talk is going to be invited from Jeff Spake from Carnegie Observatories. If you want to come on up. Yeah, there's a clicker. Do you want walking microphone? Are you happy to stick near here? Yeah. So I should have done this before. So cut that somewhere near the top. Yeah.
Jess, clip it up as high up as you can.
Yeah. And then clicker. And Jess is going to tell us a tale of tales. So take it away.
Sweet. Hello, thanks so much for being here. I heard there was karaoke last night. Man, these are my collaborators. If I hear that any of you went to karaoke without me.
So if you had finished your talk.
Don't out me like that. Come on, man. 2 a.m. emails, don't. Thank you, seriously, though, for all these collaborators. I have missed out some people, but these are the main suspects. Oh, I don't have presenter notes. We'll wing it. Atmospheric mass loss is a fundamental process in understanding the habitability of the universe. It is also so important to the population of exoplanets that we've discovered today that its dramatic effects have led to the impossibility of some planets existing. These are all of the close-in exoplanets we've discovered. Distance to host star, planet radius. We have a lot of hot Jupiters up here, a lot of tiny Earth-like planets down here, and then a big gap here. This is the hot Neptune desert. So the planets that are born in this region here should be much easier to detect than those Earth-sized planets below them. This is not a selection effect. This is a real dearth of exoplanets. And we believe that this space is carved out by catastrophic mass loss. So we think that planets that are formed in the hot Neptune desert lose their large hydrogen-helium envelopes and fall down to those smaller planets down here. However, mass loss is very difficult to understand to us today. It is still very difficult to predict exactly which exoplanets are undergoing measurable mass loss. And by measurable mass loss, I mean observable signals we have with our telescopes today that we're able to place error bars on mass loss rates in a rate of grams per second. And the reason for that is because it is very difficult to observe mass loss on exoplanets directly, and it's very complicated to model. Let's start with this one. So in my work, I use the transit technique. When planets pass in front of a star, we can observe a large atmosphere in strong absorption lines of species in their upper atmosphere. This beautiful cartoon was made by Abigail Tumberang, who worked with me when she was a summer student. She's now started a PhD in cosmology in the Netherlands. I won't hold that against her. The way we observe mass loss in exoplanets is via these very strong absorption lines. So here I'm showing, for context, an image of the Earth taken a broadband UV wavelength in the 1980s with NASA's Solar Dynamics Explorer. You can see a large halo that extends thousands of kilometers above the Earth's surface. And this glowing red halo is neutral hydrogen. You can also see the aurora glowing in oxygen. There's a broadband image that covers these oxygen lines, and the strong Lyman alpha line that corresponds to the jump between the ground state and the first excited state of neutral hydrogen. So in these regions that you can see up here, the density is 14 orders of magnitudes lower than the density of the atmosphere at sea level, which is about 1 kilogram per meter cubed. This is very rarefied material, and this is where we can actually see the material escaping. But in order to do this, we need very abundant species with very strong absorption lines, like this Lyman alpha hydrogen line. Yeah, where's my timer? Is that says 20? 20 minutes left. Gotcha. All right. Oh, okay. And it was this very strong absorption line of hydrogen that was used to detect the very first escaping atmosphere, HG 209458b, which is a hot Jupiter on an orbit of 0.05 AU and equilibrium temperature of about 1500 Kelvin. Not surprising that it's losing its mass. In the optical broadband, its transit depth is about 2%. You can see this light curve here. But when this planet was observed in the Lyman Alpha line with Hubble Space Telescope by Vidal Majar in 2003, 3 times they observed this transit, and they saw a repeatable transit depth signal of order of 10%. You see it's much lower than this optical here. This suggests that there is a large cloud of material surrounding and escaping the planet which overflows its Roche radius, which is the sphere of gravitational influence of the planet. And so this planet is undergoing rigorous escape. A little bit of detail about this Lyman Alpha line. Why it's difficult to observe. So it's a single strong absorption line, the strongest in many stellar photospheres. Wait, not photospheres, many stars. However, it has this double peak shape, and that's because we cannot observe the core of the Lyman Alpha line because there's hydrogen in between the stars, and that absorbs this flux. Also, that glowing geocorona that I showed you around the Earth, that also interferes with the core of this line. So you have this double peak shape. We're not able to access the rest wavelength of this line. We can only look in the wings of the line, and specifically the blue wing of the line, where that's material streaming towards us. This spectacular result from GJ436b, which is about the size of Neptune, transit depth of 0.5% in optical, but in these blue wings of the Lyman Alpha line, the stellar Lyman Alpha profile is this white line, and during transit, the profile is this purple line here. So there's a cloud of material that blocks out 50% of the starlight in this blue wing of the line. And it looks like this, the light curve. I'd also like you to note that here is the light curve, here are the white observations. The absorption continues many hours after transit, which are those, this is where we expect the optical transit here. What this means is there's a massive cloud of material that is escaping and is trailing behind the planet. Note that also the absorption we observe is in the blue wings of the line, and up to, wait, let me show you, up to 100 kilometers per second. This is about 10 times faster than the speed of sound in the upper atmosphere of this planet. What is accelerating this material so fast towards us? This has been a very big question in our subfield. Because of all these observational difficulties, and the fact that you can only really do this for the closest planets, because eventually the ISM just blocks out all of the Lyman Alpha flux, depending on where you look in the sky, there have only been so far 5 published detections of escaping atmospheres with Lyman Alpha. Some of you in this room may have others up your sleeve. But it's been very difficult, really, to measure direct measurements of mass loss with the main tool that we have. I will note also that there are other lines that you can study mass loss with. The similar problems persist in that one thing I didn't mention is that there are many, many surprising non-detections, both in Lyman Alpha and in other lines that are indicative of mass loss. Planets that we expect to lose a lot of mass, we go and look at with these special lines, and we see nothing, no deep transits. Why is that? As I said before, it's also complicated to model. And that's part of the reason is that blue shift I spoke about, that what is accelerating this material so fast towards us has been confusing. There are many ways that you can do this. You can do this with radiation pressure. Like this twirly thing, I wrote down the name of what this is, but I don't have my presenter notes. But you know this twirly light thing, what I'm talking about here. Radiation pressure. There's also ram pressure from the bulk of the stellar winds that can push an escaping cloud out towards us. There's also these things, energetic neutral atoms. In this case, that is when a proton from the stellar wind collides with the planetary atmosphere and strips away an electron from the material in the planetary atmosphere and carries on towards us at a very high velocity. For hydrogen, it has to be neutral for us to observe this Lyman alpha line. So you can create that Lyman alpha line at high speeds with these ENAs. These things are all very complex to model simultaneously. We've had some 3D simulations of escaping atmospheres, but these take weeks to run an individual model. I love this study by John McCann in 2019, where they put very realistically, well, much more realistic, stellar wind treatments into their exoplanet mass loss models. And they found that when you increase the stellar mass loss rate, you carve out the escaping material into these post-transit tails, which leave very significant changes in our observables. Although they also found that there is not a monotonic relationship between the stellar mass loss rate and the planetary mass loss rate. So this is complex physics which imparts huge signals on the planetary atmosphere, which we really struggle to make measurable measurements of exoplanet mass loss with error bars. This is a video from this work that I also love. But the bottom panel shows a side-on view of the planet as it transits a star. Look at this in the blue wing of the Lyman alpha line. You see absorption here, a dip, and another absorption peak a few hours after transit. I want you to remember that for later. This is from their 3D models. There's also a problem with stellar winds. The fundamental problem, actually, in stellar astronomy is that we don't have many measurements, direct measurements of stellar mass loss rates either. We can get these also with the Lyman alpha line, where the astrosphere crashes into the ISM. You also get Lyman alpha emission with this stellar wind, and you can use that to back out stellar mass loss rates. So far, there have been kind of this many measurements for regular stars, and you can see an empirical fit to this trend where we have didn't mean to press that. Increasingly active stars tend to have strong stellar winds, except when you reach this break where you get really active, and then it's a whole mess over here. It's very hard to predict stellar mass loss rates. Note this dot, GJ436b. This is an exoplanet. This exoplanet was used to place constraints on the stellar mass loss rates. And I want to do more of this and populate this plot for the star people as well. And we can do this with other lines. This is a work I did a couple of years ago where we observed a cloud of helium escaping the exoplanet WASP-107b, and we also saw post-transit absorption after the transit ended. This orange model comes from a 3D hydro simulation that I actually showed in the beginning from Wang and Dai. They also included a stellar mass prescription, and they found that the only way they were able to match the observations, I should note James Kirk also observed evidence for a tail as well, the only way they were able to match the observations is by increasing the stellar mass loss rate to 10 times the rate of solar. Note there were no error bars on this here, because each one of these models took weeks to run. It's difficult to observe, complicated to model. So in 2022, I was really pleased to see this paper by James Owen, Ruth Morrow Clay, and others, where they attempted to break down these Lyman alpha transits into the simplest physics possible, where they took a parcel of gas, this is a side-on view, they took a parcel of gas that gets launched from the planet. It's subject to the forces of gravity of the planet and the star, those energetic neutral atoms that I told you about, and also, it's also subject to the influence of the stellar wind coming at it as well. What they found is that the transit depth in the Lyman alpha line is not a good indicator of mass loss rate. It actually tells you much more about the ionization of the material and also the gravity of the system. What does tell you more about the mass loss is the length of the post-transit tail, because this can tell you how far a neutral hydrogen atom can travel along the tail before it gets ionized and no longer becomes visible. They argue that this is really a key observable for measuring mass loss rates. One interesting prediction that came out of this relatively simple model, which they could use to explore large parameter space, is that there are some kind of planets, high gravity planets, which can show double transits. This was also seen in those previous hydro models that I showed you earlier. This is because the dense material around the planet mid-transit, it's very dense and you have a lot of energetic neutral atom interactions. It is also can be high enough pressure to move some of the broad absorption line of the Lyman alpha into that blue wing of the line. So I'm talking about how we observe high blue shift. I should have mentioned. This is a light curve in the blue wing of the line. How do we get that blue shifted flux? It's from a combination of energetic neutral atoms and the high density of the escaping material during mid-transit. But then as you move away from the core of the planet, the density of the material decreases, and so you lose absorption. But then the acceleration, the ram pressure of the stellar wind gets strong enough that it accelerates the material into the blue wing of the line again, and you get a second transit. This was a key hypothesis to test what is the actual physics that is involved in these escaping atmospheres. HD 209458b is a high-gravity hot Jupiter planet with a Lyman alpha detection, and its observations stopped at the end of its transit. HD 189, also hot Jupiter, same thing. When I saw this paper before, I emailed James Owen, and I was like, oh my God, you've just told me exactly what I should observe when I write a proposal. He was like, yeah, Park's already doing one. So we got one hot Jupiter each. I got HD 209, Park got HD 198. He can talk to you about that another time, maybe. It's more complicated. I'm going to talk to you about this one today, which Park also helped me with the analysis. These are the previous observations. Ethan recently has been updating this simple model. Well, it's not like that simple, but it's as simple as we can get. He's made it much more physically consistent. A particular thing he's done especially is he's kind of allowed the tail to move further away from the planet than it was able to do before in the previous setup. He's also spent a lot of time setting it up so that we can actually use these models to do MCMC fits to real data. And he has some work on that. So he's used it to analyze some previous observations. He ran this model for HD 209458b with some different planetary, that's eta, this is a mass loss efficiency, different planetary mass loss rates basically, and different stellar wind strengths. And what you can see is that the onset, this dip here, of the second transit is very dependent on the stellar mass loss rate. Because if you have a fast stellar wind, you can accelerate it quickly. The length of this tail is much more dependent on the planetary mass loss rate, much more than the planetary transit depth at mid-transit. So this is what we aim to observe with HST. I'm sorry to the star people here. Also, actually, Ethan, you were out last night at karaoke, weren't you? You were, where are you? I knew it. I'm glad you're here still. Anyway, I'm sorry for the stellar people. This is very hand-wavy. One thing that's good about HD 209 is that it's a sun-like star and is not very active. This is a random chunk of Lyman alpha emission from the sum of the solar disk over a period of 1 year. It's not stable. It goes up and down. Very hand-wavy. It looks like it goes up and down maybe on the order of about 14% once every half period, half of 27 days. HD 209458a, our host star, has a rotation period of about 11 days. If I assume that it varies, big assumption, like the sun on maybe 10 days instead of 27, in our chunks of observation, we should expect variations in the Lyman alpha line on the order of 1%. That's smaller than our error bars, much smaller than error bars, and smaller than the size of the escaping planetary material that we expect. This is some raw data from actually this is from Vidal-Major 2003, but ours looks very similar. This is what the actual data looks like when you get it from HST. It's when it goes to the reduction. This most prominent feature is not what we're interested in. This is the geocoronal emission, that glowing material around the Earth that I showed you before, in the core of the Lyman alpha line. So this axis is the wavelength axis. This stuff here, that is the Lyman alpha line of the star itself. That's what we're interested in. We have to correct for this geocoronal emission. This dot here is a silicon line over here. Both of these lines will brighten in a flare, a stellar flare. Parker's checked. There is no evidence of flares in any of our observations. It looks like HG209 is not a very flary star. It looks like we've missed flares, so that's good. This is a zoom in of some of the raw spectra, no normalization here, from one of our visits. This is the blue wing of the line that we're interested in here. These edges, so a complex part of this process is there is going to have to be some normalization because the stellar Lyman alpha line is not constant. So what I've just done, this is debatable how good this is taken these, the flux in these edge bins and normalized everything by the average of all of the out-of-transit spectra that we have in those two bins here. This is the best we can do. So here are the previous observations taken in 2003. We had 3 HST visits, and this is what they look like. 1, 2, 3. So by my eye, this looks like there is evidence, at least some evidence for this hypothesized double transit, which has never been seen before in an exoplanet. This is also the first ever transiting exoplanet that we ever discovered in 2000, and its escaping atmosphere has been, known about for 20 years, and this is the first time we've known that it has what looks like a post-transit tail, but also this characteristic double transit feature that was hypothesized by these models. We're in the process of using Ethan's code to fit this data, so I still don't have errors for you on either the mass loss rate or the stellar or planetary mass loss rate, but that's what we're aiming for. It does look like a reasonably good match to one of our forward models, though. And this was with a actually fairly low mass loss efficiency compared to what you'd expect from the energy limited case. You don't actually need a super strong mass loss rate to get a detectable signal. What you do need is hydrogen atoms that are neutral for long enough for you to observe them. That's what to me has been key in these last few years. So to me this kind of validates the physics of how we actually get this blue shifted absorption for this Lyman alpha line. It's a combination of ENAs, the broad wings of the line, the dense material surrounding the planet, and then the gradual ionization of the materials and the acceleration of the material trailing behind the planet. So hopefully in the future, we can use this to get much better mass loss rates. Instead of running these 3D hydro simulations that take weeks to run, we can do a Bayesian fit to this evidence in about the same time. So in summary, I'm 1 minute early, sorry. We've seen evidence for HG209's double Lyman alpha tail, which is the first time we've seen this double tail on an exoplanet. To me, this seems to validate those 3D star-planet mass loss models and tell us what physics is actually happening, which hopefully now we can use to get much better star and planet mass loss rates. Thanks.
Thank you very much. Questions? Yes.
Thanks very much. Your forward model had a 1.5 solar mass loss rate in it. And I'm just wondering, how does that compare to the mass loss rate predicted from the X-ray flux with Brian Wood's relation?
Oh, that's a great question I don't know the answer to. I didn't check, sorry. Maybe we can figure that out from the... Oh, I should have... Good question. I should have known that. Ethan, do you know? Go ahead there, sorry. You don't know? Oh, that's a really great question, yeah. We could... Yeah, even maybe by eye we could have a go at having a guess. Thanks.
Bad question instead.
Oh, no.
If you had to quantitatively judge the mechanisms that differentiate between, or the mechanisms that are responsible for the forward tail and the backward tail, what's the fundamental difference, and you know, in terms of what you know, like, what's the most important one, what's the least important one?
Yeah, great. That is a good question. Don't worry. You're doing great. So for... did I show it? Oh, yeah. Here we go. When there's a weak stellar wind, you can see that a torus... When there's a weak stellar wind, there's nothing pushing away the material. And a torus of material can form at the orbit of the planet. If you increase it a little bit, it starts to push it away, but there's this like forward pressure from the atmospheric mass loss that comes out anyway. So you can get a leading tail kind of just from like a weaker stellar wind. You can see some leading tails. There are some strange observations where it looks like sometimes there's a leading tail and no post-transit tail. And I think there's a combination of things that can do that. There is this really awesome work by Fabienne, I forget, what's Fabienne's second name, do you remember? Never mind. Antonia Aklopci had a graduate student, Fabienne, and she did this really cool test of what happens when you... She did a much thorough test of different mass loss rates coming from the day side and the night side of the planet, and she found that a much hotter day side compared to the night side, and combined with the rotation of the planet, can give you a much stronger, like kind of forward pre-transit tail. Also, I think it might be some magnetic fields sometimes, but we won't talk about that because that's not in a lot of these models. I think sometimes there is magnetic connection, and that can drag some things. That's my conspiracy theory, but yeah. Thank you.
Yeah, that's good.
Thanks, this is really cool. Tim Betting, Sydney. Firstly, I Googled your whirly tube. It's called Crookes radiometer, but I'm really sorry it's not radiation pressure. They say it's a gas thing.
Oh, is it?
Yeah, so sorry.
Oh, you know what? I totally believe you. Yeah, it is, isn't it?
It's Wikipedia, but not me.
Don't listen to anything I've said.
But this is a post-truth world, so don't worry, just keep
Thanks.
going. I have a question, though. How long would it take, in an extreme case, for one of these hot Jupiters to lose a significant, like, say, 10% of its mass? Is it, like, detectable in population studies?
So for the hot Jupiters, basically, you won't. The amount of mass that you'll lose, over its lifetime, you'll barely notice. No change in radius, really, like over the entire lifetime of the solar system. It changes very drastically if you just move a bit further, well, just a bit further down, to like Neptune. Neptune-sized planets, they are very susceptible to catastrophically losing there, based on the stuff that we've observed, what we've observed so far. Yeah, for hot Jupiters, they have detectable signatures, and we can use it to, figure out the physics, but these aren't at risk of losing, of becoming destroyed this way, as far as we can tell.
Thank you.
We have time for one more quick question. Ethan, do you want to?
So do you expect all the other planets with mass loss to have this effect?
Oh, is that David?
Yes.
Hello, sorry, can you say that again?
Do you expect all the ones where you have detected mass loss, do you expect them all to have a second transit?
Oh, that's a great question. No, the fact that it goes up again and then down, that seems to be really quite specific to these high gravity planets, where there's like a big drop off in the density. The lower density planets, it just all kind of like fizzes up. And there's no like down, then up, then down again. But they do have, if the tail, the important thing I didn't mention is, yeah, the ionization really matters. If the host star ionizes the stuff too quickly, you won't see it. It's very key that it's not too ionizing. In that case, then you will see a tail, but not the up and down.
Okay, let's thank Jess again.